When you or I go to the doctor and there's something wrong, maybe like a weird pain in your knee or, a recurring headache or even a frightening flutter in your chest, there is this deeply comforting expectation that the doctor is going to take a picture of it.
Right. Yeah, absolutely.
We want to see the jagged white line of a broken bone on an X-ray. We want the specialist to, point to a glowing screen, tap a specific gray blob and say, right there is the problem.
Because seeing is believing. Right.
Exactly. Seeing is believing. We are incredibly visual creatures, so we just assume our doctors need to be visual too.
It is entirely human to want that visual confirmation. I mean, we rely almost entirely on our visual processing cortex to, make sense of the world around us.
Right.
If something isn't categorized into the shapes and edges and colors we naturally recognize, it feels like it almost doesn't exist. We really want our medical data to look like a biology textbook.
We do. We totally do. But today, for you listening, we're going to challenge that very comfort zone.
Yeah, we are.
We're taking a deep dive into a massive paradigm shift in how we think about medical diagnostics. Because it turns out, forcing a machine to draw us a pretty human-readable picture might actually be the exact thing that is holding modern medicine back.
It's a completely counterintuitive thought at first glance, I know.
Yeah.
You would assume a clearer picture always means a better diagnosis.
Obviously.
But when you look at the cutting edge of diagnostic research, and I mean the absolute bleeding edge, bypassing the picture entirely, is undeniably where the future is headed.
It's wild. And we have a truly fascinating paper on the docket today to explore this. It's from a team of researchers at the Technical University of Munich and Imperial College London.
A really stellar team.
Yeah, and I just love the title of this one. It's called, perfectly enough, No Image, No Problem, End-to-End Multitask Cardiac Analysis from Undersampled K-Space.
It's a great title, very to the point.
Our mission for this deep dive is to figure out how artificial intelligence is radically rethinking how we diagnose complex heart conditions. And it's doing this by, skipping the actual picture part of an MRI entirely.
Entirely, just throwing it out.
Right, and instead analyzing the raw, invisible, native data that the machine spits out. And we are going to explore why relying on this invisible data is the key to faster, cheaper, and vastly more accurate medicine.
It really is a game changer.
Okay, let's unpack this. Because before we get to the AI magic and how it works, we really need to set the stage. We need to understand why the current system for taking an MRI of a human heart is fundamentally broken.
Right. And to really grasp the problem, you have to look at what the medical field calls the reconstruct then analyze pipeline.
Reconstruct then analyze, okay.
Yeah. Let's put ourselves in the shoes of a patient. When you go in for a cardiac magnetic resonance imaging scan, a CMR, the machine is not actually snapping a photograph of your heart like a camera.
It's not like an X-ray where it's just a flash of light.
Right, exactly. An MRI is essentially a giant, incredibly powerful magnetic sensor.
Right.
And the raw data those sensors capture isn't spatial. It doesn't look like a heart at all.
Right.
The data is captured in the frequency domain, which physicists and doctors refer to as K-space.
Right, K-space. It's basically the native language of the MRI machine, isn't it? It's just listening to the magnetic resonance frequencies of the water molecules in your body.
That is a really great way to put it. It's listening, not looking.
Listening, got it.
But here is where we hit a massive operational bottleneck in hospitals all over the world. Capturing high-resolution, perfectly complete K-space data takes a very long time.
Because it's a ton of data, right?
A massive amount. And if you are trying to image a heart, you are dealing with an organ that is constantly moving. It's beating. Your chest is rising and falling with your lungs.
All right, you're a living, breathing human.
Exactly. So to get a clean, unblurred scan, the patient has to hold their breath.
And if you've ever been inside an MRI machine, you know exactly what that's like. You are slid into a tiny claustrophobic tube. The machine sounds like a mix between a 90s dial-up modem and an industrial jackhammer.
It is incredibly loud.
So loud. And then a voice comes over the intercom telling you to hold your breath and stay perfectly still. You can only do that for so long, especially if you are an elderly patient who is there because you already have a heart condition.
Precisely. The biological reality of the patient completely conflicts with the physics of the machine.
That makes total sense.
So, because of that human limitation, plus the astronomical hourly costs of operating an MRI machine clinics, employ a standard practice called undersampling.
Undersampling, which means what exactly?
Well, to save time and spare the patient from endless breath holds, the technicians intentionally skip collecting a massive chunk of that K-space data. They basically speed the machine up, and as a result, they gather a highly incomplete set of frequencies.
So we are starting the diagnostic process with missing data right out of the gate?
Yes, we are essentially taking a partial snapshot.
Wow. Okay.
And this is where the current pipeline really shows its inherent flaw. The medical community takes that incomplete, low-dimensional, case-based data, and they run it through some very heavy, complex mathematics.
To try and fix it.
Exactly. Specifically, an algorithm called an inverse Fourier transform. The goal of this math is to force that missing raw data into a fully reconstructed, high-dimensional, human-readable image of a heart so a doctor can look at it.
Let me make sure I'm wrapping my head around the mechanism here. We take an incomplete set of frequencies.
Right.
We use a mathematical formula to essentially guess or smooth over the missing pieces, just to inflate it into a high-resolution picture.
That's pretty much it.
It sounds like trying to unbake a cake to figure out the exact recipe, but you only have half the cake to start with.
The unbaking the cake analogy hits the nail on the head. You are asking the math to make huge assumptions. You've hit on the mathematical paradox the researchers point out in this paper. Reconstructing a fully sampled, perfect image from undersampled, incomplete data is what mathematicians call an ill-posed problem.
Because there's not enough info.
Right. You are forcing a very low-dimensional input to artificially inflate into a highly complex, high-dimensional output a dense array of millions of pixels.
Oh, wow.
And inevitably, when math has to guess the missing ingredients of your cake, it introduces errors. In MRI terms, we call these artifacts. You get visual ghosting, blurring, and information bottlenecks.
So the picture is technically a lie, or at least a heavily smoothed over guess.
Yes. And the craziest part to me is why we are doing this.
Right. We do all of this heavy mathematical lifting, introducing all these errors and blurry guesses, just so a human doctor or a downstream AI can look at that highly complex image and extract a single low-dimensional disease label.
Exactly.
The ultimate goal is just a simple output, like, yes, this patient has coronary artery disease, or no, their heart volume is normal.
Which highlights the sheer inefficiency of the whole process.
It really does. I mean, it's like taking a tiny compressed ZIP file on your computer, blowing it up into a massive, blurry billboard on the side of a highway, just so a doctor can drive by, look at the billboard, and read a single word off of it.
That's exactly what it is.
Why not just read the words straight from the ZIP file?
Right. Why endure the data loss and the distortion of blowing up the billboard when the true foundational answer was sitting right there in the native code? That is the exact thesis of this research.
But wait, I have to push back here, because this goes back to our comfort zone as humans. Doctors still need to see the heart, right?
Well, they feel they do.
Yeah, I mean, a cardiologist needs to understand the anatomy, the volume of the ventricles, how the blood is flowing. How can you possibly diagnose a complex physical geometric cardiac issue from a ZIP file, from raw radio frequencies?
It sounds impossible.
It does. If you actually look at the raw case-based data, what does it even look like to the human eye?
If you look at the visual data provided in the source material, case-based looks absolutely nothing like a human organ.
Nothing at all.
Nothing. If you look at standard spatial MRI images, your short-axis or long-axis slices, you see the distinct muscular walls of the heart. You see the chambers.
Right, the stuff we recognize.
Exactly. But case-based, it looks like a fuzzy, starry, static-filled square.
A static-filled square.
Yeah, it is incredibly bright in the very center, which is where the low-frequency contrast information lives.
Okay.
And then it fades out into a chaotic, dark scattering of static toward the edges, which holds the high-frequency fine details and edges.
So it's literally just noise to us.
It is purely a frequency domain. It is completely unreadable and meaningless to the human eye.
The starry, static-filled square. That sounds like a broken television screen.
It does. But mathematically speaking, it is the perfect dual representation of that anatomical reality.
Crazy.
Oh yeah, every single geometric detail of the heart, every curve of the ventricle, every millimeter of tissue thickness is perfectly hidden within those frequencies.
Wow.
And this is what perfectly tees up the researcher's solution. If human doctors cannot read the starry sky of K-space, we need to build something that can.
Right.
So they developed a novel representation learning framework called k-MTR, which stands for K-space multitask representation.
k-MTR. And the entire goal of k-MTR is to bypass the blurry billboard entirely.
Entirely. It is the very first representational learning framework designed to completely skip the image reconstruction phase.
Amazing.
Its sole purpose is to extract those clinical labels, to map the anatomy, and to classify diseases directly from that undersampled, static-filled K-space.
Just reading the raw data.
Right. What's fascinating here is that, mathematically, extracting a simple disease label from undersampled K-space is a much more sound, well-posed problem than trying to invent a fully sampled high-resolution picture from it.
Because you aren't forcing the math to invent pixels.
Exactly. It's a dimensionality reduction problem. You are going from messy data to a simple answer, which is something artificial intelligence is exceptionally good at.
So we are essentially teaching an AI to become fluent in the native language of the MRI machine.
That's exactly it.
But to prove that you can diagnose a patient from a blurry star map, we really have to look under the hood of this AI.
We do.
The researchers outline how k-MTR actually pulls this off, and they do it through a brilliantly designed training process.
3 stages, right?
Yeah, 3 stages. The architecture they built is incredibly elegant. The first stage of teaching the AI is all about independent learning.
Okay, independent learning.
The system uses tools called masked autoencoders. Now, without getting too bogged down in the computer science,
Please don't, for my sake.
think of matched autoencoders like digital flashcards for the AI. The system takes the data, artificially blacks out chunks of it, and forces itself to predict what the missing pieces should be.
Like fill in the blank.
Exactly. During this first stage, the AI learns the image domain and the K-space domain completely separately.
Yeah. It learns the visual patterns of spatial images on one side, and separately it learns the mathematical frequency patterns of the K-space static on the other.
It's like putting the AI in a school where it learns Spanish in one classroom and Japanese in a completely different classroom, completely isolated from one another. It's just building a basic foundational vocabulary in both languages.
That is a perfect analogy. But the next step is the crux of the entire paper. This is the cross-modal alignment stage.
Alignment, making them talk to each other.
Right. The AI creates what is called a shared latent space. You can think of this as a semantic manifold, or more simply, a shared bilingual brain where both of those languages finally meet and interact.
Okay, I like bilingual brain.
So, the system takes a fully sampled spatial image, meaning perfect, complete visual data showing the exact anatomy of a heart, and it pairs it with the undersampled K-space data, the incomplete staticky frequency data of the exact same heart.
Okay, I am tracking with you. So the AI has the perfect picture in one hand and the compressed, incomplete ZIP file in the other.
Exactly. And then it applies a mechanism called a contrastive loss function.
A contrastive loss function?
In simple terms, this function acts like a strict teacher. It forces the AI to align these two completely different inputs inside its latent space.
Wow.
It mathematically forces the system's brain to recognize that this perfect, beautiful image of a heart and this messy, incomplete square of static mean the exact same thing anatomically.
But hold on, this is where my brain gets stuck.
Okay, hit me.
If the K-space data is undersampled, meaning it literally has missing information because we sped up the MRI scan to save the patient from holding their breath, how does the AI know what is going on anatomically?
It's a great question.
Like, you can't mathematically align two things if half the puzzle pieces are missing from one of the boxes.
And that question brings us to the absolute genius of the researcher's design. Because the undersampled K-space is strictly forced to match the perfect, fully sampled image in the AI's brain, the K-space encoder is forced to implicitly restore the missing data itself.
Wait, it just figures it out.
It has to. The researchers refer to this as a latent restoration. Because the AI must arrive at the complete anatomical picture to satisfy the math, it learns to hallucinate or mathematically infer the missing anatomical signatures directly into its own code.
It hallucinates the missing anatomy.
Yes. It completely bypasses the need to draw a picture for us, but internally, it maintains the perfect 3D geometry of the heart.
That is staggering. It is like giving an actor a script where half the pages have been ripped out.
Yeah.
But because that actor has watched 1,000 perfect movies before and understands the deep structure of storytelling, they can just magically understand exactly what the missing pages were supposed to say without ever having to actually write the missing dialogue down on paper.
That is a brilliant way to conceptualize it. The AI preserves the critical diagnostic, meaning the semantics, without the computational burden of explicit pixel-by-pixel reconstruction, which then brings us to the final stage, end-to-end analysis. Once that shared latent space is perfectly aligned and the AI deeply understands the anatomy, the researchers attach lightweight, task-specific decoders to the end of the system.
Okay.
These decoders are not asked to draw pictures. They simply look at the raw, aligned K-space frequencies and directly predict the disease or the heart volume.
Here's where it gets really interesting because, dreaming up a clever mathematical theory in a pristine laboratory environment is one thing.
Oh, for sure.
But proving that this works in the real world on actual human hearts with all their quirks and variations is a completely different ballgame.
It really is.
How did they test if this hallucinating frequency reading AI actually works reliably?
Well, they did not cut any corners on the testing phase. They tested it at a massive scale. The researchers utilized the UK Biobank dataset and ran a controlled simulation on 42,000 subjects.
42,000 subjects. That is a massive data set.
Yeah, it's huge.
That is not some small 50-person pilot study to test a hypothesis.
Not at all. And what makes the test even more robust is how they treated the data. To make sure this wasn't just working in a sterile lab setting, they introduced synthetic phase variations.
Phase variations.
Basically, they injected realistic magnetic field distortions and the ambient electronic noise that you would inevitably find in a chaotic, real-world hospital setting.
Oh, to make it messy. I love that.
Exactly. Then, to keep the AI honest, they kept a strictly held-out test set of 1,000 subjects to see how k-MTR performed when it encountered raw patient data it had absolutely never seen before.
And the results. This is the moment of truth. Does reading the ZIP file actually beat looking at the billboard?
The results were incredibly validating for the team. Let's break it down by looking at a few different medical tasks. First, phenotype prediction.
Phenotype prediction, meaning what?
This involves measuring the mechanical properties of the heart, like its volume and its pumping efficiency.
Got it.
The researchers compared k-MTR, which, remember, is only looking at raw, undersampled, missing frequencies, against an upper bound AI model that gets the ultimate unfair advantage. Looking at perfect, fully sampled, high-resolution spatial images.
The gold standard.
Right. And k-MTR performed practically identically.
Wait, identical?
Pretty much. For instance, they measured the left ventricular ejection fraction. This is a crucial metric for heart health that measures how well the heart pumps blood with each beat.
Okay.
The model, looking at the perfect, complete pictures, had a very low error rate of 2.95, as you would expect. But k-MTR, operating in the dark on raw, missing data, scored 3.14.
3.14, that's barely a difference.
Right. It scored so closely to that error rate that the difference was statistically negligible. It essentially matched the perfect image model stroke for stroke.
Wow. So for basic mechanical measurements, it is spot on. But what about actually catching a disease?
It was the same story. When it came to disease classification, k-MTR matched the heavy, computationally expensive image-trained models. It achieved a highly accurate 0.737 AUC score for identifying coronary artery disease.
That's incredible.
But perhaps the most impressive result came when they tested it on segmentation.
Segmentation, remind me what that is.
Segmentation is the process of mapping out the exact, precise, physical borders of the heart's anatomy. And they tested k-MTR on this at an extreme acceleration factor of R8.
Let's pause on that. An acceleration factor of 8. That means the MRI machine was sped up so much that it collected 8 times less data than a full standard scan.
That is correct. 8 times less data.
That's barely anything.
I know. It's a massive reduction in the time the patient spends in the tube. But even with that wildly incomplete snapshot, k-MTR achieved a 0.85 dice score.
Is that good?
It means it had an 85% overlap with human experts who were tasked with drawing the borders of the heart for perfect pictures.
Unbelievable.
It essentially mapped the complex anatomical structures beautifully and accurately, relying on just a tiny fraction of the raw frequencies.
Okay, those results are phenomenal. But it makes me wonder, is this actual magic or does the system have a breaking point?
Oh, it definitely has a breaking point.
Surely if you keep turning the dial and keep taking away more and more data, eventually the AI just throws its hands up and fails.
It absolutely does. And the researchers wanted to find out exactly where that line was drawn. They ran an ablation study to pinpoint that breaking point.
How far did they push it?
They tested acceleration factors of 2x, 4x, 8x, and finally 16x.
15x.
Yeah. At 16x acceleration, meaning you were missing a staggering amount of the case-based data, the information loss was finally too great for the AI to overcome. It began to fail at predicting specific mechanical phenotypes.
So the hallucination stopped working.
Right. The latent geometry just wasn't there anymore to be restored. This proved to the researchers that the 4x to 8x acceleration range is the real reliable sweet spot for future clinical application.
Which is still an incredible leap forward for diagnostics. But, there is still a lingering doubt I have, and I imagine you listening might be thinking the same thing right now.
What's that?
If the AI is successfully diagnosing complex diseases from raw, starry frequencies, how do we know it actually understands the physical shape of the heart? How do we know it isn't just making really lucky statistical guesses based on random noise patterns?
That is the ultimate existential question in machine learning, isn't it?
Mm.
Is the algorithm actually reasoning and understanding the structure of reality? Or is it just blindly curve-fitting data to get a reward?
Exactly.
Well, the researchers anticipated this exact skepticism, and they performed an ultimate validation check to prove their case.
Oh, I can't wait to hear this.
Remember, k-MTR operates entirely without the standard inverse Fourier transform. It never uses the specific mathematical equations required to build an image.
Right, it bypasses it.
But just to see what the AI knew inside its latent brain, the researchers attached a simple image decoder to it. They basically tapped the AI on the shoulder and said, okay, show us your work. Draw the 3D object you're thinking about.
And what did it draw?
It perfectly generated a high-resolution spatial image of the heart.
No way.
Yes, it scored a 38.18 dBs PSR, which means it drew the physical anatomy down to the millimeter, perfectly matching the output of top-tier, highly specialized image reconstruction models.
Without ever doing the math to build a picture.
Exactly. It proved, beyond a shadow of a doubt, that it implicitly understood the full 3D geometry of the human heart, relying solely on its interpretation of the raw, invisible frequencies.
That is wild. It essentially proved that it had the perfect blueprint memorized the whole time. It drew the perfect billboard without ever being taught how to use a paintbrush.
Right.
It just naturally knew what the physical reality had to look like.
If we connect this to the bigger picture, the implications of this blueprint for you, for the listener, and for the global healthcare system at large are massive. This paper lays the groundwork for what the authors call task-aware MRI workflows.
What does that actually mean for the everyday patient lying on the MRI table?
It means a fundamental change in the patient experience. It means drastically shorter breath holds. If we only need an 8x undersampled scan to get a perfect life-saving diagnosis, patients spend significantly less time trapped in that loud, claustrophobic tube.
Which is a huge relief.
And that dramatically reduces the operational cost of MRI clinics, which makes the technology vastly more accessible to communities that currently can't afford it.
Right, accessibility is huge.
And clinically, it means we are moving toward a future where we use AI systems that don't get confused by the visual artifacts and blurring that we humans accidentally create when we force raw data to conform to our visual biases.
That is just so profound.
The next step for this technology lies in expanding this framework to what they call prospectively acquired multi-coil data sets, which basically means taking this out of the simulation and applying it to real-world multi-sensor clinic data on a global scale.
So what does this all mean? When we zoom out, it means that the native, invisible language of our medical machines is actually the purest form of diagnostic truth. By forcing the machine to speak our visual language, by demanding that it draw us a picture, we were actually losing the plot and muddying the waters.
We were introducing noise, simply to comfort our own biological need to see things. k-MTR proves that if we just get out of the way and let the AI analyze the data natively, it doesn't just compensate for our missing pieces. It understands the intricate geometry of the human body on a deeper mathematical level than our own eyes do.
Which leaves me with a final, slightly provocative thought for you to mull over today as you go about your life. If an AI can perfectly understand and diagnose the complex life or death realities of a human heart directly from a chaotic, static-filled square of raw radio frequencies data that is entirely unreadable and meaningless to the human eye, what other invisible raw data streams are flowing around us right now?
Wow, yeah.
Think about the acoustic frequencies of your car engine as you drive down the highway, or the ambient Wi-Fi signals constantly bouncing off our bodies in our living rooms. What incredibly complex, perfect truths about our world are hidden in that raw data that we are currently ignoring or ruining just because we're obsessively trying to translate them into something our limited human senses can understand.
It really does make you question how much of reality we miss simply because we demand to see it first.
It really does. Thank you so much for joining us on this deep dive. Keep questioning the reality of the information around you, and we'll catch you next time.